Hello, this is Mrs. Scarpel with an updated video for topic 2.15, semi-log plots. We did a little of this, I believe, in topic 2.9, but this lesson is going to take us even further into semi-log plots. So what is a semi-log plot? It's a graph in which one of the axes is logarithmic scaled. In this course, that axis will always be the vertical axis or the y-axis. The other thing about semi-log plots where the y-axis is logarithmic scaled, the exponential functions will appear linear. So if we take a look at these two graphs here, on the left, we have a graph that shows the population of English Americans in the current United States from 1620 to 1820, where t equals 0 represents the year 1620. So this is the population using a normal scale. On the right, the y-axis, or the vertical axis, has been scaled logarithmically. And as you can see, what appears to be an exponential curve is more linear on the logarithmic scaled graph. So, using the features of the semi-log plot above, justify why the exponential model is appropriate. It's as simple as saying when the y-axis is logarithmically scaled, the data appear linear. This means an exponential model is appropriate. So when a semi-log plot appears to be plotting points in a linear fashion, an exponential model for the points is appropriate. Here, we're going to take a semi-log plot and find out what the exponential equation is. So what I'm going to do is I'm going to create a table of the first 3 points because I can see exactly where those points are. The next 3 points look to be where I'd have to guess a little. So I'm going to create my input, which is going to be my X, or actually in this case it's T. So we've got Mr. Passwater telling a joke. P people have heard it. After T minutes. So we're going to have a table that's T and P of T. So T is the number of minutes. P of T is the number of people that have heard the joke. At minute 0, 2 people heard the joke. At minute 1, we have 2, 3, 4 people have heard the joke. And at minute 2, we have 5, 6, 7, 8 people have heard the joke. So as an exponential model, I can see when my input values are increasing. I have equal length input values. My output values are increasing proportionally. That means I'm multiplying by the same value to get the next value. In this case, I'm multiplying by 2. So when I look at my functions down below in my options, I've mentioned this is going to be an exponential model, so it's not going to be C. A is a linear model. It's not going to be A. For B, yes, it is exponential in that it has 2 to the power of t, but we're not shifting these values up another 2 values, so it's not going to be B either. If we look at D, we have our constant ratio of 2 to the power of t, and we have that initial value at time 0 of 2. So the answer is going to be D. And now I'm going to skip ahead to example, I believe it's example 5, yep. But before we complete example 5, there's some other information we need to know. So given the exponential model, y equals a times b to the x, we can write a corresponding linear model for the semi-log plot. That corresponding linear model, so the rate of change, that constant ratio, the b, we're going to do log base n of b, so that value that is causing that constant change also becomes sort of our slope. It's the log that comes in front of the x. And then the initial value, the a, is our y-intercept or our vertical intercept, but in this case we're going to say log base n of a. And n has to be greater than 0 and it cannot equal 1. So the slope of our function is log base n of b and the y-intercept is log base n of a. The base of the logarithm corresponds to the base used for the scaling of the vertical axis. So in the case of example 5, our semi-log plot, because we're seeing powers of 10, that means our base of our semi-log plot is also going to be 10. Now, to find the slope so that I can write a linear model, I need 2 points. So I'm going to use the point at 1 and the point at x equals 2, because I can see where they are exactly. However, when I do the rise portion, it's not just, okay, that's 2 more. We have to use the log of those values. So we're going to do log. I'm going to use the one at 2 first. So log of 20, 30, 40, 50, 60 minus the log of 20, 30, 40 over 2 minus 1. So this is finding our average rate of change, or our slope. I'm going to simplify this. I have the log with the same base with a difference. So that's going to become log of 60 over 40. And 2 minus 1 is just 1, so I don't really need to worry about the denominator anymore. But one thing I can do with this log is simplify the 60 over 40 to 1.5. So we're going to have the log of 1.5 be our value for b. So this is going to be our slope, our log base n of b. Now we also need to find what log base n of a is. Again, I need to use my graph, but I'm also going to use my log base n of b to help me find that log base n of a. So I'm going to go ahead and I'm going to use the point at 1. So my y value is actually log of 20, 30, 40. So we're going to say that log of 40 is going to equal our log base b of n. So our log base b is log of 1.5 x plus log of a. Then I can, oh, I forgot to substitute for the x. Excuse me, I knew I was missing something. Once I replace x with 1, I can solve this because that's my input for the log of 40. There we go. Well, I know that log of 1.5 times 1 is just going to be log of 1.5. So to get log of a by itself, I'm going to do log of 40, and I'm going to subtract the log of 1.5. And that's going to equal my log of a. Now again, I have two logarithmic statements or expressions with a difference, common base. So we can write this as log of 40 over 1.5 equals log of a. We can also take 40 and divide it by 1.5 because it isn't best practice to leave a decimal within a fraction. So this can be written as log of, I'm going to take my calculator and do 40 divided by 1.5, and I'm going to leave it in its exact form. So I'm going to do math, and the first option highlighted under math is fraction. So I'm going to press enter, and that's going to give me this quotient as another fraction, as another rational number. So we're going to have log of 80 thirds equals a. So what is our equation in the form y equals log of b times x plus log of a? It's going to be y equals log of b is log of 1.5 times x plus log of 80 over 3. So that's our equation, our linear equation from the semi-log plot. Now I can use the a and b from that semi-log plot to complete part b, which is writing it as an exponential model. As an exponential model, we're going to have y equals, remember the a value is the y-intercept, so it's going to be 80 thirds. And the b value is our slope, or the value that's within our slope, and that's 1.5 to the power of x. And that's our equation in the exponential model. We can go back and forth from these two models as long as we know the a and the b, as long as we know what a and b are. And this concludes the video for topic 2.15.